Hey everyone, welcome to another exclusive video tutorial by Scalar Academy. Before moving forward, please subscribe to our channel because a lot more tutorials are coming up and you don't want to miss them.
In this video, let's talk about the problem trailing zeros in factorial of n. As per the problem description, we are given an integer n and we have to return the number of trailing zeros in factorial of n. So please note that your solution should be in logarithmic time complexity. As per the problem constraints, n lies between 1 to int max, and in the example input we are given n as 5. The example output is 1 because the factorial of 5 is 120. Here there is only one trailing zero. So therefore we will simply return 1. Now what is a trailing zero? So if you look at here and if you say there are 3 trailing zeros, then you are wrong. Why? Because a trailing zero is the one which is at the rightmost end and that has no non-zero number to the right of it. So here there are only 2 trailing zeros. This will not be counted as a trailing zero. Let's see how can we approach this problem. So the brute force solution to this approach is that first we can calculate the factorial of n and then count trailing zeros in the result. So we can find the trailing zeros by repeatedly dividing the factorial by 10 till the remainder is 0. So what do we mean by that? So let's say the factorial, the n is equal to 10 and we'll do 1 into 2 into 3 into 4 into 5 into 6 into 7 into 8 into 9 and into 10. This will give us the number as 3628800. Now to find the trailing zeros, we will simply mod it with 10 to get the last digit. So we will get 0. Now since this is 0, we will simply increment our count. Next, we will divide the number by 10 to check the next number, the next digit, that means this number. So after dividing it, we will get nothing but 362880. So that means this digit has been removed, the last digit. Now we have got this. Now in the next iteration, we will simply do the mod of it to get the last digit. We got it as 0. So again, we will increment the count. Next, we will divide it by 10. Right, so here we have divided it by 10. Again find the mod of it and we get a non-zero number. That means here we have to stop because we have found out all the trailing zeros. And since we have got a non-zero numbers, that means we do not care what is there at the left of it, right? So we will simply stop and return the count. And this is what written in this snippet, that we have got the factorial as 120 of 5 when n is 5. So we will run our loop till this factorial is greater than 0. So if f mod 10 is equal to 0, we will simply count it up and we will divide f by 10. And else if it's not 0, then we will simply break because we do not care what is there on the left and we will simply return the count. But the problem with this approach is that the above method can cause overflow for even slightly bigger numbers, as the factorial of a number is a big number. So even if the number is as small as, let's say, 22, then it's going to cause overflow because the factorial of even a small number is so big that it is certain to cause overflow, right? Therefore, this method is not the appropriate one. So what should we do now? Let's see what is a better approach. So how can we find a trailing zero in any number? So when a number is multiplied by 10, we get a trailing zero, right? So let's see 24. If it's multiplied by 10, we get 240. So here we have got a trailing zero just because we have multiplied it by 10. Then we have, let's say, 240, and if we multiply it by 10, we get 2400. We have got another zero which is contributed by this 10. Right, so in 2400, if we do into 10, we will get 24,000. So another zero which is contributed by 10. So here there is an observation to make that a number, if multiplied by 10, it will give us a trailing zero. So for example, if n is equal to 10, then we'll get this as this is the factorial of 10. So 1 into 2 into 3 into 4 into 5 into 6 into 7 into 8 into 9 into 10. The factorial is this, and we can see that there are 2 zeros, the 2 trailing zeros. That means there must be 2 tens, right? There must be number of tens is equal to 2 that are contributing to 2 zeros. So how are we getting that? So 1 10 is here and 1 10 is formed by the combination of 2 and 5. So if we multiply 2 and 5, we'll get 110, right? So this is 110 and we will get 110 from here. So that accounts to 2 zeros. So this tells us that if in a number we look at the number of pairs of 2 into 5, then we'll be able to count the number of trailing zeros. So if in a number we look at that how many number of 2's are there and how many number of 5's are there, then we take the smaller number, we take the smaller power of a number. Let's say 2 is x and 5 is y. So let's say y is smaller than x, then we will take this, the number of 5's, and that is going to be the answer. Why? Because let's see with the help of this example. So in this case, the power of 2 is 3. That means there are number of 2's as 3. So this is 1 and 2 into 2 gives us 4. So 1, 2, 3. So there are 2 3's and 5 is just 1, right? So 5 will pair up with a single 2 to form a 10. Therefore, we will look at a lesser power from between 2 and 5, right? Now, do we really need to find the power of 2? Do we really need to find a power of 2? Well, here the observation is to be made that if we carefully look, then every second number is a multiple of 2 and every fifth number is a multiple of 5. So, if we are just able to find the power of 5, then they can pair up with that many number of 2's to produce a trailing 0. So let's look above with the help of example. So in this case, every alternative number, so this is a multiple of 2, then this is a multiple of 2, 6 is a multiple of 2, 8 is a multiple of 2, then 10 is a multiple of 2. So at every second number, we are able to find the multiple of 2, which will give us the number of 2's, right? That will give us the number of 2's. And every fifth number is going to be the multiple of 5 that will contribute to a power of 5, right? That will contribute to the power of 5. So as we can see that the number of multiples of 2 are greater than number of multiples of 5, that means we are going to get more number of 2's as compared to 5. So the number of 2's are going to be greater as compared to the number of 5. So we need not calculate the power of 2. Instead, we can simply calculate the number of 5's or the power of 5. So the problem has now reduced to finding the power of 5. So this is a generalized equation, like if we want to find a power of any number, then we can apply this formula. Here our x is equal to 5. So here we are actually trying to find the power of 5 and let this be any number, the remaining number which when multiplied with the power of 5 gives us factorial n. So how can we find the power of 5 or how can we calculate the number of 5? So for that purpose, we can simply take the floor of n by 5. For example, let's say n is equal to 11. Now n by 5 gives us 2.2. The floor of 2.2 is nothing but 2. That means the factorial of n is going to have 2 zeros. If we see here, then the factorial of 11 is nothing but 3991680. So there are 2 zeros, the 2 trailing zeros. Because in 11, how many multiples of 5 are there? It's 5 and 10. So this has contributed to 1 5 and this has contributed to 1 5. Therefore, the total number of 5's are 2 and therefore the trailing zeros are 2. But we are not through yet. Why? Because what about if n is equal to 28? What will happen in that case? So if n is equal to 28, so in 28 factorial, what are the multiples of 5? So the multiples of 5 are 5 itself, then 10, 15, 20 and 25. 5 will contribute to 1 5, then 10 will contribute to another 5, 15 another 5, 20 will also contribute to 1 5, but here 25 is going to contribute to 2 5's. So by taking floor of n by 5 with the formula n by 5 and taking floor of it, we'll get 1 5, right? So if we do n by 5, that means 28 by 5. This is going to give us 5 only, right? So that means here we are going to get just 5 zeros. But here we can see that there are 6 zeros in total. So for getting the left out 5, that means the 5 which is still to be counted, we'll have to divide it by next power of 5, which is 25. So now we actually have to calculate the power of 25. But now what about 128? So in that case, we'll get 125 as well in the multiples of 128 factorial, the multiples of 5 in 128 factorial. So it's going to be 5, 10, 15, then 20, 25, 30 and so on. Then 125 as well, right? So 125 has 3 number of 5s. So after dividing by 5 and then by 25, we'll still be left with one more 5. So for that, we'll have to divide it with the next power of 5, which is 125 to actually get the third 5. Now the formula has become, so the count of number of 5s in prime factors of n factorial, it's equal to floor of n by 5 plus floor of n by 25 plus the floor of n by 125 and so on till the number is greater than n by power of 5. So the time complexity of this approach is going to be order of log base 5n. What was the question? That we have to find a logarithmic time complexity, and we have actually achieved that. So why? Because we are incrementally dividing n by powers of 5. So first we are dividing n by 5, then n by 25, then n by 125, so on till n by 5 to the power k, which reduces to 1, and n by 5 to the power k is equal to 1. So n is equal to 5 to the power k. After taking log both sides, we will get k as log base 5n. That means log base 5n number of steps we have to take to get the solution, and therefore the time complexity is going to be order of log base 5n. So this was it. Let's talk about the problem anagrams. So given an array of strings, you have to return all groups of strings that are anagrams. Represent a group by a list of integers representing the index in the original list. Let's look at this sample case for clarification. So an anagram is a word, a phrase or name formed by rearranging the letters of another. For example, spar and rasp. Both are anagrams because they have same set of characters, the frequency of characters are same, but only the order is different, right? Also note that all inputs will be in the lower case. So for example, the input is cat, dog, god and TCA. So you have to return 1, 4 and 2, 3. So basically we have cat over here, then dog, then god and TCA. So this is 1, 2, 3, 4. Right. So cat and TCA, they are anagrams because they have same set of characters. Even the frequency is same, but the order is different. Right. So we have taken them together. That means 1 and 4 are together. Likewise, dog and god, they both are anagrams because again the characters are same, the frequency is same, but the order is different. So 2 and 3 are anagrams. So we have to basically return the answer like this. Now here in the explanation, it's written that cat and TC are anagrams which correspond to index 1 and 4. Dog and god are another set of anagrams which correspond to index 2 and 3. So the indices are 1 based. The first element has index 1 instead of 0. So let's see how can we approach this problem. So the solution approach is that we can sort the given strings. Now how does this intuition came? So basically from the question itself, it said that anagrams are the words that have different order of the same set of characters. So if we sort both the strings, then if those strings become equal, that means they are anagrams, right? Because the order was different only, but they have same characters. So if we sort them, then the strings which are anagrams will become equal. And after that, we can simply group them together, right? So here we have got the input as act, DGO, DGO and act. So we have actually got them by sorting the individual strings given in the input. So ACT represents cat, DGO represents dog, and DGO again represents God, and ACT represents TCA. Right, so we have basically sorted them. Now we know that a group of anagrams can be represented by a key, which is nothing but the string we get after sorting characters present in those strings. Right? So here both cat and TCA are anagrams and they can be represented by a string which is ACT. So this we have got after sorting the characters present in them. So now to group the strings basically, we can perform hashing. So how can we do that? So a key can be the string, right? This unique string. Here the group of anagram is cat and TCA, right? So we can have a unique string for them which is ACT. Likewise for dog and God we can have a unique string as DGO. So we can have a string and then we can have value as vector of int because we have to basically keep track of the indices of the anagrams, right? So now we will simply iterate over this array, the sorted array. So first we are at act, then act is not present in our map. So let's put the string and the index present is 1. So let's put it in the vector, right? Now we are at DGO, right? So DGO is also not present in the map. So let's put it in the map and the frequency and the index present is 2. So let's put it in the vector. Now let's move ahead. So DGO is already present in the map. Now let's include the index, right? So we have included 3. Now we are at the 4th position and act is already present in the map. So let's simply include the index. So here we have the set of anagrams represented by their indices. Now the only task is which is left, that is to iterate over them and store it in the vector, right? So here we have vector 1 and 4 and we have a vector 2 and 3. So we will push them into a vector and we will simply return this in our answer, right? Also we will only put the vector in this resultant vector which have a size of greater than 1, right? If a string has size of if the vector has size of just 1, then that means there is no anagram present for that particular string. So we can simply ignore that, right? So now for the time complexity, let's look at how we are going to sort the strings. So for sorting the string, basically we can perform counting sort. We are able to perform counting sort because here the range of characters is fixed, right, which is 26. So we have 26 characters and therefore the complexity is going to be order of n into k, where n is the number of strings and k represents the length of the longest string. So the time complexity turns out to be order of n into k. Now if we don't want to sort the strings up, then we have another approach as well. So we can actually maintain a frequency array, right? Now what is a frequency array? So let's suppose we have this as a string. To form a frequency array of this, we will have a character set. We will have an array of 26 characters which have a range from 0 to 225. So why 26? Because we are in the input we are given that only lowercase alphabets will be there, right? So we maintain a frequency array of size 26. Now basically we will be mapping small a to index 0, then small b to index 1 and so on, and we will be representing small z by index 25. So basically here we will be storing the frequency of all the characters. So frequency of 0 denotes that it is the frequency of character a and so on. Here the frequency of a is nothing but 1. So we will put 1 over here. Then frequency, so basically we will be iterating over the string, so let's do that. So here b is there and frequency of b is nothing but 1. So at index 1 we will put 1. Now b is nothing but only 1, so let's put 1 at index 3, right? Then a is there, so let's put 1 at index 0. Then c is there, so let's put 1 at index 2, and e is there, so let's put 1 at index 4. Initially all will be initialized to 0. So here's how we have built this frequency array, and likewise we can do for this string as well. And if the frequency array of both these strings come out to be equal, that means they are anagrams of each other. And likewise we can check this for all the strings given in the array. So for this purpose, we can basically have a map where the key can be, instead of string, it can be the vector of int. So here it represents the frequency array. The strings having the same frequency array will be pushed to the corresponding vector. So let's see how we will maintain this. So here we have cat, right? Frequency array for cat will look something like this. So here in this will be the key, right? Since was not present, so first we will be pushing it, right? And then we will be placing this one over here. Then we will be moving on to dog, and frequency array of this will look something like this, and we will simply put 2 over here, right? Then we will move on to god, right? The frequency array of god will look something like this, so we will put 3 over here. And for TCA, the frequency array will look something like this, so we will put 4 over here. So that's how we can do it, and then the last thing left will be to simply iterate this like we did previously and return the answer. The time complexity for this approach is going to be, so for creating frequency array for a string, it's going to be order of k, where k is the length of the string, and the total time complexity will be order of n into k, where n is the number of the strings, so it's going to be order of n into k. So this was it. Thank you so much.
Hello everyone. So I'm Naman Bhala. So today I will be solving two problems from binary search, and let us say one other problem, that whatever comes in my mind. Okay. So let us solve the problem of, let us say that we will solve the matrix median and we will implement the power function. Let us start with the matrix median. The problem says that we are given a matrix of integers A, the name of the matrix is A, and the dimensions of the matrix are n cross m, okay, in which each row is sorted. Okay, so basically each row is sorted, and we have to find and return the overall median of the matrix. No extra memory is allowed, and rows are numbered from top to bottom, and columns are numbered from left to right. Okay, so basically we have to take order of one space to find the median of the matrix. Median of matrix is nothing but the the middle element of the whole matrix. Okay, and if the total number of elements in the matrix are even, then it is the it is the mean of the two middle elements of the matrix. Okay, we're only given the matrix A. Is it given that the total number of numbers will be odd? No, right? That is not given. So okay, n into m is odd. It is given that. Okay, so it is always going to be the middle element of the whole matrix. Basically, the element, I mean, like in equal number of elements are less than that element, and equal number of elements are greater than that element. Okay, so that element will be the answer. Okay, so this is an extension of a very simple binary search question, which is known as find median of an array. But this has some optimizations. Okay, first of all, let us see how we solve the find median of an array question. Suppose we have to first find the smallest and the largest number of the matrix. The largest number of the matrix will be any of these three, right? It can be 5, it can be 9, or it can be 9. Why? Because all the rows are sorted. Similarly, the smallest number can be any of these three. Okay, because it is not given that elements are individually sorted, but only the rows are sorted. Okay, columns are not sorted. So it could have also been a 1. So first we find the smallest and the largest element. How we can do that? Let us say minimum element is initially int max, and maximum element is initially int min. Okay, so we do for int, let's first calculate the dimensions of this. N is equal to a dot size and m is equal to a0 dot size. Okay, Now we've tried to find the minimum and the maximum element of the whole matrix. So I say for int I equals to 0, I less than n plus plus I, minimum is equal to min of the present minimum, comma, ai 0. Okay. Similarly, maximum is going to be the max of present maximum and ai m minus 1, right? Great. So now we know the minimum and the maximum element. So once we know the minimum and the maximum element, what can we do? Once we know the minimum and the maximum element, now we can binary search to find, which can be the answer, what can be our answer, right? So let us say initially the answer will be a number in the range of minimum to maximum, right? So because all the numbers are within that range. So let us say L is equal to minimum and R is equal to maximum. Okay. Initially we don't know the answer, so we set the answer variable by -1. Okay. Now we try to do the binary search. Okay. By the way, in binary search, I always try to maintain one template, the exact template that I'm writing now, because this avoids all the what we say as overflow issues and infinite loops as well. So this template works perfectly fine. Okay. So now we need to check if there are less than or equal to n into m by 2 elements for mid, right? If there are less than or equal to n into m by 2 elements, then this mid. How can we do that? Then one way to do that is we have to iterate over the whole arrays, over all the rows and all the columns, and we try to find how many numbers in the matrix are less than or equal to mid. Correct? That is one way. The other way is because all the rows are sorted, rather than traversing, we can actually binary search over each of the row and find how many numbers are less than or equal to the mid, right? We can find that in order of log n. So how can we do that? Let us say that one of the rows is currently, let us say 1, 3, 5. Okay? So let us say the row is 1, 3, 5. And suppose our mid is 4. Now, how many numbers in this row are less than equal to 4? 2, right? There are 2 numbers in this row that are less than or equal to 4. What we can do is we can binary search upon this matrix and we can find the first index greater than mid in the row. Okay. So basically first index in this case will be 2. Okay. And basically whatever will be the first index that will be greater than mid, that is our answer. Correct? Okay. Now what are the edge cases? The edge cases that index 0. Let us say suppose our mid was 0. In that case, 0 would have been the answer. So that is perfectly fine for us. But there is also an edge case, no element is greater than mid, right? In that case, we should assume, answer is equal to n. What I mean by n is basically the number of elements in the row. Okay. So for example, it can be 0, it can be 1, it can be 2. And let us say, had there been a 3 here, probably that would have been the largest element. So we can say that this 3 is the answer. Okay. So now we have to binary search upon each row and find in the whole matrix how many elements are less than or equal to mid. Okay. So let us say less equal count is initially 0. Okay. Then I will do on each row, I will try to do the binary search. Okay. In this row also, I will have to find L, which is, let us say 0, and R will be equal to M minus 1. And answer can be considered to be, it's a normal binary search, so answer can be considered to be initially M, right? Because if none of the elements are less than equal to mid, M is the answer, right? This is actually M, not N. Okay. So how will we do the binary search? I will again do the same. While L is less than equal to R, int mid is equal to L plus R minus L by 2. Okay. Now what are the cases? The very first case is if array I mid is less than, or I have to make this mid 2, right? If array I mid 2 is less than equal to mid, that means either answer is equal to mid 2, or in that case, this will actually find me the last element that is less than equal to mid, right? And L is equal to mid plus 1. Okay. else r is equal to mid minus 1. Okay, but I have to find the very first element that is greater than mid. Okay, how can I do that? Let us actually change it a bit. Let us say that if array I mid 2 is greater than mid, in that case I set answer is equal to mid 2 and r is equal to mid minus 1. Else L is equal to mid plus 1. Why am I doing this change? Because I need to find the very first index that is greater than mid. So suppose the element at this particular index is greater than mid. Now either this can be the answer or the answer is somewhere to the left, right? So if I do it this way, then I will satisfy the property and then I can say less equal count plus equals to answer. Okay. So now at the end, I will know how many elements are less than or equal to the current mid, right? This should be r is equal to mid 2 minus 1 and this is should be equal to L is equal to mid 2 plus 1. Now I have to check if less equal count is what? If the less equal to count. So let us say that I'm like for a matrix, what should be the answer? Suppose our matrix is this 1, 2, 3, 4, 5. So if the elements that are less than or equal to this are, in this case, n is equal to going to be 5. If the elements that are less than equal to mid are what we say, what is going to be 5 by 2? 5 by 2 is going to be 2, right? 5 by 2 is going to be 2. So I have to find the first index for which this is equal to 3, right? Okay, so I can say if less than equal to count is greater than mid plus 1, greater than I mean like n by 2 plus 1, then this can be the answer or answer can be somewhere to the left. Okay, so I can say if less than equal to count is greater than or equal to n into m by 2 plus 1, in that case my answer can be mid or it can be somewhere on the left, right? R is equal to mid minus 1, else L is equal to mid plus 1. Now my answer will be the real answer and I can finally return answer, right? Because I'm setting this here. Will it work? Yes, it is the correct answer. Yeah, here I have done one bad coding practice. I'm using the same variable names here as well, right? But why this is going to work? Because I mean like the upper L and R are not really going to be affected, right? Ideally, this should have been a different function in itself, okay? A function, I mean like this thing actually should have been something like a function that has two parameters. I mean like that can be integer less equal count to which you pass the array A and you pass the mid, and this returns count of numbers less than or equal to mid. So ideally this thing should have been abstracted into a function, but I haven't done that. Why? I mean like just to be a bit fast, okay? But as you see that the answer is correct and I think even in submit it should be fine. Correct, we got 218 points. In binary search, I mean like just an advice, always try to I mean like use this template because this is always going to work perfectly fine. And I mean like you have to only remember one template in your mind, so that actually helps you a lot. So what we are doing here is we are in this particular case, right? In this particular case, we are trying to find for each row. I mean like this for loop is running for each row. For each row, I am trying to find number count of elements that are less than equal to mid, right? Why can I do that? Because each row is independently sorted, right? As each row is independently sorted, I can do a binary search over each row and find the count of numbers that are less than or equal to mid. Okay. So how it helps me is that now in how much time can I find the count of numbers that are less than or equal to mid? I can find this in order of n log m, right? Otherwise, I mean like had I not done a binary search, it would have taken me order of n into m time. Okay. Now, what is the overall time complexity of this algorithm? This loop, this while of L is less than equal to R loop runs for order of log of maximum minus minimum, right? Basically, that is the range of numbers. So the overall time complexity is going to be order of n log m into log of maximum minus minimum. Got it? I'm finding the count because I need to find which is the number that is the median of this matrix, right? Now, which is the number that is going to be a median? The median is that number. I mean, like the count of numbers less than equal to that is equal to the count of numbers greater than equal to that. Okay. Now, how can we find the number is equal to count of numbers that is greater than equal to that? We can do a binary search, right? Because I mean, like, why can we do a binary search? So definitely we know that, I mean, like, let us say this matrix. Okay. Suppose X numbers are less than or equal to 6. Then we are definitely sure that more than that greater than X number are going to be less than equal to 9, right? So as this property is a monotonous function, that means we can use binary search to find the index. Okay. I mean, like, I'm not sure if you have seen this question, find median of an array, find median of an array, median of a constant array. Okay. If the array was not constant, you could just sort it and then find the middle element, right? But suppose you were not allowed to modify the array, then what you can do is you can use binary search over the answer range. Okay, cool. Okay, what this does is, so the very first thing is we are given that each row is individually sorted, right? 135 is sorted, 269 is sorted, and 369 is sorted. Okay, but it is not that 5, I mean, like, the element at this place is less than equal to element at this place. Okay, only the rows are sorted. Okay, now you are asked to find which number in this matrix is going to be the median. I mean, like, suppose you would have converted this matrix to an array. What is going to be the median? The median is the element that is the middle element of a whole array, right? Okay, so basically median is the element. Suppose an array of size n is sorted. Okay, so let us say that the array was 1 2 3 4 5. Okay, middle is going to be, I mean, like, for this case n is equal to 5, right? Middle is going to be nothing but the element at the index n plus 1 by 2. Clear? Okay, so that is what the median is going to be, right? Median is going to be the element at this particular index, which in this case is 3. Okay, awesome. Actually, the third element or the element at index n by 2. Index is going to be n by 2. N by 2 in this case will be 2, and 2 is this particular index, right? Okay, so that is the median element that is going to be. But how can we search for this element? Now, suppose I try to do a binary search. The question then changes to finding the n plus 1 by 2th smallest element of the array, right? I mean, like, I'm not sure if you have seen this question as well. All these questions follow the same property. Find kth smallest element of the array. Okay. This question is a very, I mean, a popular question of binary search. Okay. A median problem is nothing but find kth smallest, where k is nothing but n plus 1 by 2. Right? This is what the problem reduces to. Now, what code I'm doing here, this code is nothing but the code to find the kth smallest element of the array. Okay, so that is why I try to, I mean, like, if I do go here, I try to find if, I mean, like, if this is greater than equal to k, then I do. I mean, like, this is the exact observation that you do. I mean, like, let us actually discuss the kth smallest problem as well. Kth smallest element has a lot of ways in which you can solve this. The very first way in which you can solve this is sort the array and return a k minus 1, right? This has order of 1 space, but order of n log n time. Okay. Okay. The second way is use a priority queue. Use a heap or priority queue. Okay. This has order of k space and time complexity of order of n log k. Correct? The third way in which we can do that is binary search. Binary search allows you to do this in order of 1 space and time complexity of order of n log of range. Okay, so in the questions when you are not allowed to use an extra array, in the questions when you are not allowed to use an extra array or extra space, in this case the binary search works. Okay, also in some cases you might not be allowed to modify the array. In that case you can't use sort, right? Unless you create a copy of the array, which you don't in most of the languages, right? So I'm like, this will have order of n space only if you are not allowed to modify the array, because in that case you will have to create a copy of the array, right? Cool. So actually, if you have not seen this question before, try to solve this particular question as well, kth smallest element, in all the three ways. Okay, using the array, using a heap, and actually I'm like, if you want to solve it in even a better way, there is also quick select. Quick select allows you to find this in order of n probabilistically. This intuition is just like intuition of quick sort. So there are multiple ways to solve this simple problem. Okay, so if you actually encounter this problem in an interview and you tell all these ways, person will be impressed. Okay, cool. Do try to solve this question. After this question, also try to solve this question. Find median of an array. When you will solve this particular question, you can solve this in binary search on answer way. Okay. Then the question that we solved today, find median of a matrix, is nothing but an extension of the web question, extension of median of an array. Okay, cool. I think let me actually explain how this quick select works, but let me just give you a brief idea of this. In quick sort, what you do, in quick sort, you partition and solve two sub problems, right? And that is why the time complexity that you get is a tree, and then you get a time complexity of order of n log n, correct? But in quick select, you partition, that is the very first step. Okay, now what are the possible scenarios after you partition? Okay, the scenario one is that partition is at an index, like pivot is at index greater than k. In that case, solve problem only of left side. Like the problem is then find kth smallest on left side. Find kth smallest on left side. Okay. And the other scenario is pivot is at index greater than k, right? At index less than k. In that case, the problem is find basically which smallest. Suppose pivot is at index less than k. Let us say that in this index is u. So the problem is just find k minus uth smallest on right side. Okay. So now the time complexity T of n is going to be nothing but T of like order of n plus T of n by 2. Right. Now this time complexity, if you try to solve this particular recursion relation, is order of n. Okay. Yes, but in this case, we will have to modify the array. So this will only works only if we are allowed to modify array. Okay. So basically, if we are allowed to modify the array, the best solution probabilistically is quick select. But I mean, like in worst case, this can be order of n square. So that is a takeaway that you have to do. So one question, it can be solved in multiple ways, right? Even if we are not allowed to, I mean, like even if we were not given a sorted array, we can use binary search to find the median, but then the time complexity that will be needed will be order of n into m into log of range. Okay. So basically, I mean, like let me give you an idea of that. Okay. How you can get an idea of that is, let us say that you were given an array like this: 7, 3, 9, 4, 2. Okay. Okay. Now what you try to do is you have to find the median element, right? So first of all, in the very first step you do, suppose you calculate a mid element. Okay. Suppose initially the L will be 2 and R will be equal to 9. Okay. So you try to see, in the case 1, you try to see, can suppose what is mid? Mid comes out to be suppose 5. Now you find how many elements are less than equal to 5. How many elements are less than equal to 5? In this particular array, only 2 elements are less than equal to 5. ठीक है, लेकिन अगर 5 को median होना था, I mean, like if 5 had to be a median, how many elements should have been less than equal to 5? 3, right? I mean, like if 5 was to be a median, So I mean, like if we would have sorted this array, this would have become 2 comma 4 comma 2 comma 3 comma 4 comma 7 comma 9, right? Acha. So if mid is 5, how many elements are less than equal to 5? 3. Okay. Acha. अगर 5 को median होना था तो how many elements should have been less than equal to 5? 3, right? Because the element that is the median, I mean like in this case 4 is the median, there are less than or equal to 3 elements. I mean like there are 3 elements that are less than equal to 4. Acha. So 5 can be the answer. So सबसे पहले mid is equal to 5. Then we do an order of n iteration over this array and we see how many elements are less than equal to this. ठीक है? अच्छा. Now when we see that okay the answer is 3. अच्छा. So if 5 would have to be the median, then how many elements would have to be less than equal to 5? 3, right? Acha, so yani 5 can be the answer. This means 5 can be the answer, but something less than that can also be the answer, right? Can also be the answer. I mean, like suppose हमारा mid would have been 7. हमारा अगर mid 7 होता, तो how many elements would have been less than equal to 7? 4, right? So शायद ये answer होता, but something smaller than that would have also been the answer. ठीक है? In the next iteration, suppose our mid comes. In the next iteration, suppose our mid comes as 3. Then we again do an order of n loop, and we see that only 2 elements are less than equal to mid. So can 3 be the answer? No, 3 cannot be the answer because अगर वो median होता, so there should have been less than equal to 3 elements that are. ठीक है? अच्छा. So now the range reduces to 4 to 5. I mean like या तो 4 होगा या तो 4 होगा आंसर या 5 होगा. ठीक है? In this case, mid will be 4. ठीक है? Now we again do an order of n loop. How many elements are less than equal to 4? 3. So that means now my range changes to 4 to 3. This is an invalid range. So my answer is 4. Okay? So this is how we solve it. So how many different mids we will have? We will have total of order of log of range mids. And to verify if a particular mid can be the answer, we need order of n time. So that is why the total time complexity is order of n log range 2. Okay? Cool. Let us solve one more question then. Cool. We will solve one backtracking question and then we will call the end of the day. Okay, so let us take this question. Palindrome partitioning is the next question. Interesting. So the question says that we are given a string S. We have to partition S such that every string of the partition is a palindrome. Okay. And we have to return all possible palindrome partitioning of S. Okay. Okay, like this is one palindrome partitioning. This is another palindrome partitioning. Okay. Then we have to order the results in such a way that smaller entries should come first. Okay. And I mean like first smaller entries should come first and yeah, so that is the only thing. I'm like the partitions should be sorted by the length. Okay, so AAB should come before AA comma B. Why? Because length of AA is greater than the length of A. So that is actually a very easy thing to do. Okay, how can we solve this question? Okay, so in any what we say backtracking question, you have to first think that about what thing will I make a decision for, right? In this case, what can I make a decision about? In this case, I can make a decision about, hey, can I partition after this particular index? Can I break the string after this particular index? That is a decision that I can make, right? Okay. But when can I partition after this particular index? When can I partition after this particular index? I can partition after this particular index only if the current string is a palindrome, right? Because I can partition only if the current string is a palindrome, right? Okay. So I mean, like, how can I check if the current string is a palindrome? One way to check that is, hey, I maintain what is the start index, where is the partition starting from, up to the end index, and then I do an order of n loop to see if that particular string that we made is a palindrome, right? Let me actually implement it in that way, and then I will try to even give an optimized version of that. Okay. Acha. So let us, I mean, like how I solve the backtracking questions. I first try to write the recursive function and then you will see that how we solve it. Okay. Recurse. What is the thing that I'm making? First of all, what is the thing that I need? Firstly, I need the string itself, right? Firstly, I need the string itself. So I will need the string A. Okay. And what is the next thing that I need? I told you that I need to know where is the current partition starting from, right? So I need to know what was the start index of the current partition. Okay. Okay. What do I also need to know? I also need to know the current index, because after that only can I make a decision that, hey, should I partition after this or not? Okay, because that is the thing I'm making the decision about. Okay. So I need the current index. Do I need anything else? I also need to store what was the current, what are all the other partitions that I've already made before the start index, right? I mean, like I already, suppose I have to make a partition at B, I already need to know that AA partition has already been made. Or I mean, like in this case, when I'm going to make the partition of B, I need to have an array where I have already stored that I have made these two partitions, right? So I can also have a, I mean, like vector of string current partitions, current parts. Okay. Awesome. Acha, what is the base case? The base case is when the current index is equal to the end index, right? So I mean, like if current index is equal to what I say a dot size, in that case probably that is the base case. I'm like, how will I solve this base case? I don't really know right now, but let us say that this is the base case. But first of all, let us try to recurse. I mean, like, what will we do for other cases? Other cases, we have two choices. The very first choice is not partition here, and the second choice is partition here. Okay. Acha. First of all, if I do a partition after this particular index, and that is a valid partition, should I first partition or should I first take the case of not doing a partition? I should first take the case of doing a partition. Why? Because that will give me a smaller value of the current string, right? Okay. So I mean, like smaller length palindromes should come first. I mean, like A should come before AA. So that is the thing that we have. That is the only order that we need to maintain. Okay. So that is why we should first take the case of partition here, and then we should take the case of not partition here. Why? Because this will lead to a larger sized current partition, right? And we'll need a larger size current partition at the end. Okay, later. Okay, cool. So first of all, let us say when can we partition? To partition, we need to ensure that the string from start index to current index is a palindrome, right? So how can we do that? So we say int L is equal to start index, int R is equal to current index, while L is less than R, and if AL is not equal to AR, in that case, is palindrome is equal to false, and I can break. Okay. Otherwise, I do a plus plus L and I do a minus minus R. That is a normal function of how you check if a string is a palindrome. Awesome. Asha. If it is a palindrome, in that case, I can do a recursion of recurse A. Start index will now change to current index plus 1, right? Because I have made the string till here a partition. So the next string will start from the current index plus 1, right? Acha. Then what is the current index? Current index is also going to increase by 1. So that is current index plus 1. What is current parts going to be now? Now I can do current parts dot push back the substring of A dot substring from the index start index of size current index minus start index plus 1, right? So I do this to current parts. So my current parts will now change to this. Awesome. In backtracking, once you come out of recursion, what do? You undo the effects of recursion, right? So what can you do here? You can do current parts or pop back. Amazing. And what is the case of no partition here? The case is simple. We just recurse A. Start index doesn't change this time. Current index changes to current index plus 1, and the current parts remains as it is. Okay. Acha. Now we have to take care of the base case. What will be the base case? I have to push this to the answer if current index is equal to A dot size and start index is also equal to the current index. Why? Because I mean, like in this case, I will do answer.pushback of current parts. Why will I do that? I mean, like if start index is equal to current index, that means there was a partition that ended till the last index, right? I mean, like otherwise there is the last part of this string that is not yet partitioned into a palindrome. Okay, what is the difference between start index and current index? Start index in this particular scenario is the index where the current partition is going to start from. Okay, I mean, like let us say for this case, I mean, like suppose our string was something like this: A B A double B A. Okay, so once we are at A, suppose start index was A. This means we are considering this part of the string. क्या ये palindrome हो सकता है? So we need to know somehow that where is the current partition going to start from. Okay, where did the last partition end basically? Okay, and current index is the particular index that we are trying to make last index of another part. That is the difference basically. Okay. Okay. So now I will need to have an answer as well. So this will be a vector of string. Answer. Okay. So if I have a global answer, I will need to clear it. Okay. And then the question is simple. I recurse from 0 to what we say recurse 0. Start index is initially 0 because the first partition is going to start from 0. Current index will also initially be 0. And then what will be the initial current parts? Initial current parts will be an empty array, right? Because initially there is no part. So we can say that current parts is empty and we can pass this current parts to the variable. Okay, great. And then we can finally return answer. Let's try to test it. I hope I have not done any issues. A comma 0 comma 0. So this should be an A. That is all. Correct. So this is working perfectly fine. And let us try to submit. Great. So yes, we are done with another question. So there is a doubt, sir. I always confuse backtracking step. Can you please explain why we pop that string if we finally need to print it? Awesome. Yeah, let me tell you. Okay. Acha. So now take this case. Okay. When will we come back to this line? We will come back to this line only, only after we have completed the recursion and we are trying to, we are back from the recursive stack, right? So that means we have already printed the answer. What backtracking helps us with is, otherwise, what were the different choices? Otherwise, first of all, you would not have passed a reference of the vector, but you would have passed a copy of the vector. Okay. Then in this case, what you would have done, you would have included this substring in the in the copy and then pass this, right? This would have been the first case. So this is the normal recursion, right? Hey, the very first part is I partition after this particular index. In this case, I include the current substring to my current parts, and the other cases when I don't include them. So this is the normal case. But what is the issue with this? The issue with this is that hey, you need to create a copy of the answer variable every time, right? You need to create a copy of this current parts every time, which adds an additional order of n complexity. Creating a copy is not order of 1, it's order of n. So if you have to do it order of 1, what you can do is basically put something to the answer. Give something, but once that particular recursive call is done and you're back, take away something from that. Take away that thing that you gave back from it. Okay. How you can do that? So basically backtracking, the general approach is in swapping question as well. So suppose in backtracking, you do swap A comma B, then you do recursion. After that, you again do swap A comma B. Okay. So the steps is something like this is do some work, go ahead. Okay. And once you are back to your life, undo that work that you had done. So taking an example with your general life, suppose you make a very bad decision in your life, then what do? First of all, you don't know if the decision that you have made is a bad decision, right? So you make that decision. So do some work is a bad decision that you made. And now you proceed with your life. At the end stage of the life, you encounter that, oh, I had done bad work. But I'm like, even if you had done good work, but suppose someone gives you an opportunity to live the life again. So what will you do? Because you have already seen a part of the life, and when you come back to the same situation, now you will take a different road. That hey, I could have also made this particular decision, right? But before you take that different road, you have to undo whatever change you had done at the previous stage of your life, right? So what can you do? I mean, like, you just first undo the work that you had done here, and then take another decision in your life. Got it? So I mean, like, in Sudoku question, that thing is more clear. In Sudoku question is first decision is, let us put 1 at current index. Okay? Acha. Then you proceed solving the remaining Sudoku. Proceed solving the remaining Sudoku. Okay. Acha. So once, suppose you are done, I'm like, suppose you have solved this Sudoku, then you will never come back to the same state of life, right? But if you later encounter that, hey, because of the decision that I had made here, I cannot solve this Sudoku now. I mean, like, I was not able to solve this Sudoku. So what will you do? The very first thing that you will do is undo whatever changes you made here, right? So undo the decision and then decide to take 2 at current index and so on. Okay? Cool. Okay, guys. So that was all from my side. Bye-bye.
Hey guys, so the first question that we are going to discuss today is the question longest valid parenthesis. And this question was previously asked in Google. So what the problem says is that given a string A containing just the characters opening parenthesis and closing parenthesis, find the length of the longest valid well-found parenthesis substring, right? So what will the input format? The input format will be just only one single string. What will the output format? We need to return the length of the longest valid parenthesis substring, right? And here you can see that the string can be of at max 75 into 10 raised to the power 4, right? So let's say this is the given example. So for this given example, the output will be equals to 2. Why? Because the longest valid parenthesis is equals to this section. Whereas in the input 2, the output will be 4 for the longest valid parenthesis as the pair of the first 2 parentheses and the second 2 parentheses. It's one of the very important questions, and this has been marked as 700 on interview bit. So let's just see that how we are going to solve the problem. Okay. So here you can see that the problem says that you need to find the longest valid parenthesis, right? Okay. So what we can surely say is a pair of parentheses will be said valid when we have the opening parenthesis balancing the closing parenthesis. So this is a valid parenthesis. Maybe we can say this is also a valid parenthesis. We can say this also has a valid parenthesis. Maybe this one is also a valid parenthesis, because here you can see that all the opening parentheses are balancing the closing parenthesis. So what observation can we make? So the first observation that we can make for sure that for any index, if the character at that index is equals to an opening parenthesis, right, then obviously the longest valid parenthesis ending at this position will be equals to 0. Why? Because this is an opening parenthesis and we need to have a closing parenthesis corresponding to it to have it balanced. Yes or no? Okay. Apart from that, let's say that if the character at any index is equals to closing parenthesis, right? If the character is equals to closing parenthesis, then there can be few cases. Let's just see what they can be. Let's say that the character of previous index, let's say the current index was I, so the previous index will be I minus 1. So if the character at the previous index is equals to an opening parenthesis, right, then here you can see that the I minus 1th index and ith index will be making a balanced valid parenthesis pair. Yes or no? So what we can say is whatever our answer for this particular index will be, this will depend on the fact that, let's say there were some characters still here, then at I minus 1th index we had an opening parenthesis, and at the ith index we had a closing parenthesis. So what we can say, the answer at I will be depending on the fact that what was your answer till the index I minus 2. Answer at I minus 2 plus 2. 2, why we are adding 2? We are adding 2 for this pair of valid parentheses, right? So whatever your longest valid parenthesis pair or longest valid parenthesis substring was till the index I minus 2, we will just add plus 2 into that, yes or no? So this will be the case when the previous index parenthesis is equals to a closing parenthesis. Now there can be a case that the character of previous index is equals to a closing parenthesis, right? So now what you can suggest here, that if this is not an opening parenthesis, instead it is a closing parenthesis, then what we can say is this will be looking like something this one. We need to find the answer for this index I, and at I minus 1 we are having a closing parenthesis. So what we can say is we need to find the counterpart of this ith index closing parenthesis somewhere to the left side. So what we can say is whatever our longest valid parenthesis will be for this I minus 1th index, the length of the longest valid parenthesis substring for this I minus 1th index is, let's say, something like this one. So what we can do is we will just add 2 to the answer of this one. Why? Because if we are able to find, let's say that if we are able to find one more opening parenthesis to the just left side of this, so what we can say is this is on and whole are making valid parenthesis, right? So to sum my statement up, what I'm saying is if you are having a closing parenthesis and just previous index element is also a closing parenthesis, then you need to find the longest valid parenthesis for this I minus 1th index element. So let's say it was looking something to this one. Now, if the just previous index, so let's say this index was X. If the just previous index element, that is X minus 1th element, is also an opening parenthesis, then can we say that this on and whole are going to make continuous substring of valid parenthesis? Yes or no? So what we need to do, we need to just check that if the previous index element, the previous index closing parenthesis is having whatever substring there it is having, just before the starting index of that substring, if I am having an opening parenthesis, then obviously I can make a balanced pair of parentheses here. So we will just add this to our answer. So what we can say is, in this case, answer at I will be equals to, we will first need to check also, that if I minus, let's say answer at I minus 1 minus 1. So this will give me the X minus 1th index. If this is greater than equal to 0, that is it exists in the string. And what I can say is or we can say str dot char at I minus answer at I minus 1 minus 1, if this is equals to an opening parenthesis. So in this case, this will be satisfied. So what we will say, answer at I is going to be equal to answer at I minus 1 plus 2 for what? 1 for this opening parenthesis, 1 for this closing parenthesis, and this will be stored in answer at I minus 1 plus whatever the answer was till this index, right? Till this index, whatever our answer was, we will add this particular subsequence, or we can say this particular substring to that particular answer. So how we will extract that answer? We can just have that as, we can have answer at I minus, answer at I minus 1 minus 2. Why I'm doing a minus 2 here? Because doing minus 1, we were getting this index. By doing minus 2, we will be getting X minus 2th index, right? So this is how we will be able to extract the answer when we are having a closing parenthesis, and just before that we are having a closing parenthesis, right? So let's just try to code this solution and see that if this logic is working or not. So let's just first extract the length of the string, right? So I'm going to code the solution in Java. So we can have int n is equals to s dot length, right? So this answer, the answer array that I was making here, this is equivalent to the DP array that we need to make, right? But before that, we need to have a check here that if n is less than equal to 1, right? That is, if the length of the string is 0 or the length of the string is 1, then our answer is always going to be 0. So no need to compute anything. Apart from that, what we can do, we can make a DP array equals to new int of size n, right? Because at any particular index, we will be storing the longest substring of valid parenthesis till this index I, right? Now, what we can say is if, let's say, char ch is equals to s dot char at 0, we'll check that what is the first index element. So if ch is double equals to a closing parenthesis, so let's say if the first character that we were having was equals to a closing parenthesis, so irrespective of this fact, we can say dp of 0 is equals to obviously 0, because for the first character there can never be a valid parenthesis string. Now we need to check for the first index character. So if the ch was equals to a closing parenthesis, right? So this ch is representing what? The 0th character index. So what we can say is, let's just instead extract this one, right? If this is a closing the closing parenthesis, and s dot char at 0 is an opening parenthesis, right? So if the first index character, so I've changed this to first index. So if the first index character is equals to a closing parenthesis and the 0th index character is equals to a opening parenthesis, what we will do, we will store dp at 1 equals to 2, because the substring length will be equals to 2, right? Otherwise, dp at 1 will be equals to 0, right? So the base cases for our dynamic programming array is set up. So now what we will do, we'll check that for int I equals to 2, I less than n, I plus plus, right? So we are going to iterate over all the possible characters, right? Now we'll extract the character as ch is equals to s dot char at I, right? Now if ch is double equals to, and so what cases we were having here? So here you can see if we are having an opening parenthesis at any point of time, if we are having an opening parenthesis, so our answer will be equals to 0. So what we can say, dp at I equals to 0. Else, if we are having a closing parenthesis, we will check that, okay? If s dot char at I minus 1, if this was double equals to an opening parenthesis, right? So this is the case where we are having the previous index element as the opening element. So what we will do, we will do dp at I is equals to dp at I minus 2. We will be having dp at I minus 2 plus 2, right? So 2 for the sake of the new valid parenthesis pair. Else, we will check that if for the current index, that is I minus dp at I minus 1, if this is greater than equal to 0, right? That is this index exists, and s dot char at I minus dp at I minus 1 minus 1, if this is double equals to, so let me just this is double equals to an opening parenthesis, right? So let me just bind this in one pair of parentheses, right? If this condition holds true, so what we are going to do, we are going to do it like dp at I is equals to dp at I minus 1 plus 2 plus, now we need to add the previous answer, right? That was present before this particular index. So we need to first check that if this the previous index exists or not. So if I minus dp at I minus 1 minus 2, if this is greater than equal to 0, so what we will do, we will add the answer of dp at, I'll just copy this one here, otherwise I'll just add a 0 in place of it, right? So we will just bind it here again, right? So at last, so whatever the maximum value in our whole dp array will be, we will just return that. So we will just do return arrays dot stream dp dot max dot get as int. So you can use this inbuilt function of arrays dot stream dot max to get the maximum element from the whole dp array or for any corresponding given array, in particularly in Java. So let's just test it. And here you can see the sample test case has been passed. So we'll just submit our solution. And here you can see that we have scored full marks in this solution, right? So I hope the logic for this problem is clear to everyone, right? Okay. So the next problem that we are going to discuss, right? Yeah, so this is the next problem that we are going to discuss today. So what the problem says is that given an array of integers a of length n, find the longest length subsequence which is first increasing and decreasing. So you will be given an array as the input format, right? And you need to return an integer representing the answer, right? And the length of the array can be as big as 10 raised to the power 7. So here you can see that this is 1 to 1. So answer will be equal to the whole array, that is 1 to 1. For this array 1, 11, 2, 10, 4, 5, 2, 1, the longest subsequence first increasing and then decreasing will be 1 to 10, 4 to 1. That is equals to the length 6. So generally, a subsequence which is firstly increasing, then decreasing is also called as a biatonic subsequence, right? So let's just see how we can solve the problem. So I guess you all might have already learned about the problem. You might have already learned about the problem of longest increasing subsequence, right? So let's just get our test case here. So 1, 11, 2, 10, 4, 5, 2, 1, right? In this array, we need to find the longest subsequence first increasing, then decreasing, right? Now, what we can visualize here is, we can find the increasing part using this LIS algorithm that we have already discussed in the previous lectures. But for this decreasing sequence, how we will be able to find this decreasing subsequence? Can we say that if we visualize the LIS from reverse direction, then this will lead us to a longest decreasing array from the previous side, right? So let's just see what I'm trying to say. So firstly, I'll make the increasing subsequence array. So for 1, the longest increasing subsequence will be 1. For 11, it will be 1, 11, that is 2. For 2, it will be 1, 2, that is 2. For 10, it will be again 1, 10 or 2, 10, that is equals to 2. Then for 4 also, so for 4, we will be having 1, 2, 4, that is 3. For 5, we'll be having 1, 2, 4, 5, that is 4. For 2 again, we will be having 1, 2, that is 2. And for 1 again, that will be equals to 1. So this is the increasing subsequence. Now what we need to do, we need to find the increasing subsequence from the reverse direction. So if you will visualize from the reverse direction, so here you can see that this is equals to 1, right? So 1 will be equals to 1 only for the longest subsequence. Now if we will just see 2, so what we will check that 2, 1 is going to make the longest decreasing subsequence, or if we can just visualize from the reverse side, it is what? 1, 2. So for 2, we will be having the answer as 2 only. Yes or no? Okay. Now for 5 again, we will do the same thing that we were doing for longest increasing subsequence, that we are at 5. We will go to the next index of 5, that is 2. Is 5 greater than 2? Yes, it is. So whatever the longest increasing subsequence, longest decreasing subsequence we were having, which was ending at 2, we can just append a 5 in front of it to make it of length 3. So we'll add a 3 here. Now we'll go to 1. So longest decreasing subsequence ending at 1 is equals to of length 1. If we will append 5 in front of it, it will be of length 2. So it is not better than 3. So we'll do nothing. So for 4 also, it will be appended to 1, 2, 5, 4. That will be equal of length 4. For 10, it will be of length 5. For 2 again, it will be of length 2. For 11, it will be 1, 2, 5, 4, 10, 11. That will be of length 6, right? Small mistake. So this was 1 to 5. Now for 4, we will be having 1 to 4, not 1 to 5, 4. Now for 10, we will be having either 1 to 4, 10 or 1 to 5, 10. Irrespective of the fact, whatever subsequence we are having, it will be of length 4. Now for 2 again, it will be of length 2. For 11, we will be having 1, 2, 5, 10, 11 or 1, 2, 4, 10, 11. So it will be of length 5. And for 1, it will be of length 1. So this is the decreasing subsequence array, where at each index I, we are having the longest decreasing subsequence, right? Now how we will be able to find the longest increasing decreasing subsequence? Here you can see that. If you will just sum up the values of both the arrays, so what we'll get? We will get a 2 here, then we'll get a 7 here, we'll get a 4 here, then we'll be having a 6 here, then we'll be having again a 6 here, then we'll be having a 7 here, then we'll be having 4 here, and then we'll be having a 2. Now, what these values are representing? Let's just consider this 6. So this 6 is representing the fact that there was a subsequence of length 3 that was increasing, and then of length 3 that was decreasing. So let's just see what was that. So we were having 1, 2, 4 as the increasing, then 4, 2, 1 as the decreasing. That's why the length here is 6. But can you see that you have considered 4 twice here? And for any valid subsequence, we need to consider all the elements once only. So we'll just subtract 1 from each index here. So this will be 1, this will be 6, this will be 3, this will be 5, this will be 5, this will be 6, this will be 3, and this will be 1. Now let's just see what these represent. So let's just take this 6. So this 6 represents that we are having a subsequence like 1, then 11, and then we are having 10, 4, 2, 1, or 1, 11, 10, 5, 2, 1. In both the cases, the length of the subsequence is equals to 3. So what we need to do in this problem is, you first need to calculate the longest increasing subsequence. Then you need to calculate the longest decreasing subsequence ending at each index. Just sum the elements of all the indexes and just subtract -1 to avoid the repetition of elements. Right. So let's just try to code our solution and see that if we are able to do so or not. So we will have first the length of the array, that is a dot size. Right. Okay. Now what we will do, we'll first make increasing DP array. Let's just mark it as DP only. So DP is equals to new int of size n. Right. Then DP of 0 will be equals to 1 always. So what we'll do, we'll start from I is equals to 1, I less than n, I plus plus. For int j is equals to 0, j is less than I, j plus plus. This is exactly equal to the code of longest increasing subsequence. Right. Now what we'll do, if now we need to check the values, right? So if a dot get I is greater than a dot get at j, right? If this value is greater than the value present at j, the current value is greater than the value present at j, what we'll do it like dp at I is equals to math dot max of dp at I, whatever solution we are having till now. Apart from that, dp at j plus 1, right? This can be a good candidate. Now we can do similar thing for a new array, right? So we'll be having a dp2 array for the longest decreasing subsequence, right? The n minus 1th index will be having a value of 1. We'll start from n minus 2. We will go to greater than equal to 0, and we'll just decrement the ith pointer. Apart from that, we will start from I plus 1th index. We will go to I less than n for jth iteration, and so on. Now again, if a dot get at I, if this value is again greater than a dot get at j, so what we'll do, dp2 at I is equals to math dot max of dp2 at I or dp2 at j plus 1, right? So this will be the corresponding solution. Now what we'll do, we'll just add both the indexes and just subtract 1 from it. So for int I is equals to 0, I less than n, I plus plus, we'll just add in the increasing array itself. So dp at I plus equal to dp2 at I minus 1, right? So this will be dp, and at last we will just return the maximum value. So we just saw that how we can just easily return in single line. So arrays dot stream dp dot max dot get as in, right? So let's just see that if the solution is working or not, or if you are not having any runtime or something solutions like that. Okay, so we need to handle one more case, that if the array is empty, what we need to do. So if n is double equal to 0, we need to handle this. So we will just return 0, right? Okay, so there is some bug. So your function returned the following, and the expected output is the following. Okay, so let's just debug once that if you are having any error or not. So we just had n is equals to 0, then we return 0. So one thing that also we need to do is we can do it like arrays dot fill. We can just fill all the indexes with 1. Why? Because for any index, what we can assume is initially when we have not computed any longest increasing or decreasing subsequence, the maximum length increasing subsequence or decreasing subsequence ending at that point is equals to 1 only. So we'll just fill this all the values with 1. We can do similar thing here as well, right? This is dp2. Okay, now starting from ith index till nth index, then from 0th index to ith index, we compared I and check if it is greater or not, and this is good. Now we will go to int dp2, and Then we will just fill this up, right? Then we'll start from n minus 2th index, go to the 0th index and decrement I. Then from I plus 1th index, go till n and increment the jth variable. Then a dot get I is greater than a dot get j. So what we are going to do, we are having this as dp2, cool. So dp2 at I is equals to mat dot max of dp2 at I or dp2 at j plus 1, cool. This is working perfectly fine. Right, now we can do this like dp at I plus dp2 at I minus 1. Okay, cool. I guess we should test it again. The sample is passing now. Okay, so we are having one issue here. So function is returning 4 and the expected return value is 5. So let's just debug it, that what's going on with this one. So firstly we'll add 5, then first number is there, and then okay. So 1, 2, 3, 4, 5. Let's just test it, that what's the exact issue here. Okay, yeah, so makes sense. So let's just debug it, that what should be going on in this particular test case, right? So at 1, so firstly, if our increasing subsequence will be starting from the 1th index, right? And at the last index, it will be storing what? 5, right? And okay, in this dp2, okay, so I got the case most probably. This is dp2 at n minus 1, that is going to be equals to 1, right? And apart from that, let me check that if I'm not manipulating dp1 somewhere. Okay, yeah, so this was a small issue, and here you can see that we have completely solved the problem, right? So there was a small bug that I was just manipulating dp1 instead of dp2, right? So I hope the logic for this problem is clear to everyone, and we will move to the next problem for today, right? So the next problem says that the problem name is max sum without adjacent elements, right? So what the problem says is that given a 2 cross n grid of integer, choose the number such that the sum of number is maximum, and no two chosen numbers are adjacent horizontally, vertically, or diagonally. Okay. So let's say that this was the case. Let's say that this was the case. So what we can say here is the output will be 2. Why? We need to choose 3 and we need to choose 5. Why? Because if we are choosing this 3, we cannot choose this 2, we cannot choose this 1 or this 3. Either we cannot choose this 2 or this 4, right? So the next choices we are having is from this particular row only, that is from 4 or 5. So at any particular point, if we are taking any element, we cannot take the vertical element or the diagonal elements or the horizontal elements, right? So let's just see how we can solve the problem. So the test case given to us is, let's just discuss using this test case only, that is 1, 2, 3, 4, and we are having 2, 3, 4, 5. 2, 3, 4, 5. Okay. So what you can say here is, if we are choosing this element, we cannot choose this 2, we cannot choose from this column, we cannot choose from this column, right? We cannot choose from this column, right? And the same thing will happen. Let's say this was the case. If we will choose this 2, we cannot choose this 3, we cannot choose anything from this column, we cannot choose anything from this column. Now for this particular column, that is the first column, we had 2 choices. Either we could have chosen 3 or we could have chosen 2. We could get a maximum value by picking up the greater element. What we can say is, for any column, we will always pick the max element. If that's the case, now this problem will boil down to the fact that from the 0th column we'll be getting 2, from the first column we'll be getting 3, from the second column we'll be getting 4, from the last column we'll be getting a 5. Now having an array like this one, what we need to do, we need to choose the element such that we are not choosing any adjacent element, right? Now this is a trivial problem to solve. Why? Because if we are choosing this element, let's say let's just discuss with 4. If we are choosing this 4, what we can say is we cannot choose this 3, right? And whatever the answer we have till this index I equals to 0, we will add 1 to it, or let's say we will add 4 to it. This is one choice, that we are picking 4. If we are not picking 4, then whatever answer we will be having at index I is equals to 1, that will be our answer. So what we can say is dp at I will be depending on the fact that what is the maximum among dp at I minus 1, that is when we are not choosing the current element, or dp at I minus 2 plus array at I. Whatever the maximum we'll be having among these two, we will be just storing that. We'll be just storing that. Okay. So let's just try to code the solution and see that what goes on. So here you can see that you will be getting an array list of array list, or in C++ you will be getting a vector of vectors. So we'll just generate the single array first. So int n is equals to a dot get 0 dot size. Right. So here you can see that it will be a matrix where we will be having two single arrays, right? So this will be something like this one. So now we'll construct the array int arr is equal to, sorry, this will be an array is equals to new int of size n. Right. Now what we are going to do for int I equals to 0, I less than n, I plus plus, right? ARR at I will be equals to math dot max of a dot get 0 dot get I, comma a dot get 0 dot get, this will be get 1 dot get I. Why I am doing this? Because there are only two rows, that is the 0th index row and the first index row, and then we will be having the element. So first we will extract the 0th index row, then we will extract the ith index element, then we will extract the first index row, and then extract the ith index element from that. So using this we will be having our array prepared. Now we will be preparing a dp array is equals to new int of size n, right? So inside our dp array, the 0th index will be equals to what? ARR at 0, right? If n is less than equal, if n is double equal to 1, we will just return this dp at 0, right? If that's not the case, so we'll keep a case here that if n is equals to 0, we will return a 0. So if these two if checks will not be executed, what we can do is we can have dp at 1, right? So what this can be, if ARR at 1 is greater than ARR at 0, we will be storing ARR at 1 here, otherwise ARR at 0 here. Why? Because if we will be picking the first index element, then we can't pick the 0th index. If we'll pick the 0th index, we can't pick the first index. So whatever the maximum we'll be having, we'll just store that in our dp at 1. And now what we'll do, we'll just do int I is equals to 2, I less than n, I plus plus. dp at I is equals to math dot max of dp at I minus 1, comma dp at I minus 2 plus ARR at I, right? And on the last index, we'll be having our answer. So we'll just return dp at n minus 1. So let's just test the solution. Okay, so sample case has been passed. Okay, so here you can see that we have successfully solved this particular question as well, right? Okay, so one piece of advice I would like to give to everyone, that as you can see that considering the fact that what situation we are having outside, utilize this time as much as possible, right? You guys can even subscribe to the channel of Scalar Academy to get some awesome content related to computer programming, including data structures, algorithms, some web development stuff, system design stuff, so on and so forth, right? So I hope that you liked today's lecture. So thank you guys. See you next time.